All right, so 11.4 is going to put together everything we've been doing except L'Hopital's rule for that 11.3. That's a little bit different concept, right? So we're going to go back to what were we covering for 11.1, 11.2, and we're going to put it all together with all of our algebra ideas for 11.4. So when we look at an equation, we should still be able to use those graphing tools that we were taught before this course. Okay, so look at this list up here for step one. Analyze that. Like, what is the domain? What are the intercepts? Are there asymptotes? We should have a general idea of what the graph looks like. If it's an x squared, we should know it's a parabola, U-shaped, right? If it's an x to the fourth, it's going to be similar to U-shaped or x to the sixth, x to the eighth, and maybe some little swirlies or something, right? A little bit different, but similar U-shaped. We should know an x to the third goes up, down, and around. If it's an x to the fifth, a seventh, an odd, right, then it's going to do something and then be, off in the directions. So there are some basic things we should know. Then we go on to step two, and we're going to use then that first derivative and all my ideas of my first derivative and find out even more about what our graph should look like. Step three, then we look at the second derivative. What does the second derivative tell us about the concave up and concave down, right? And then we can look at all that information, not our graphing calculator, and we can graph the graph, okay? This is all about coming up with how that graph should look. All right, so let's do problem one here, and we're going to apply all the things we know. I think I do it over here. I got to add a page in because when I do my Apple Pen, page. When I use my Apple Pen, I write a little bit bigger, so this is not going to be enough space for me. There we go. Then I have a blank space page. Okay, so problem one, f of x is equal to x minus 4 over x plus 4. So let's talk about that. Step one. So we have, oops, not a pencil. Step one says, I got a little cheat sheet over here. To find the domain. So let's find the domain. All right, if we look at this, do we have an x in the denominator? Why, yes, we do. Then we know there's going to be numbers that we can't cross, right? So if we look at this, x cannot equal -4. That makes 0 in the denominator. What are the other things we would look for here on domain? We would look for a square root or a log where you have to be positive and you can't be negative. Yeah, or x in the denominator. Those are like the things we look for. I think I'm missing one. No, I think I've got them all. Okay, so then that's step one, part A. We'll label this A. And then part B says, what are the intercepts? Okay, so remember we have two intercepts, x-intercept and y-intercept. So the way that we find our x-intercept is intercept, I'm spelling it wrong, is we let y equal 0. So f of x is the same as y, so 0 equals x minus 4 over x plus 4. So then we just solve this equation for that x-intercept. Well, if we take this and times it up by 0, it's going to give us 0. So really we have 0 equals x minus 4, add my 4 over, and I get 4. So x is 4, y is 0. There's one point we know has to be on that graph. Then let's look at the y-intercept. And remember, the y-intercept, you let x equal 0. Should be getting fairly good at these. So I can do f of x or y equals, you can call it y if you want. Put that down a little bit. Okay, and then we would have 0 minus 4 over 0 plus 4. Well, that's -4 over 4. So I get -1. So x is 0, y is -1. Those are just points on my graph where I cross the x and I cross the y. In business, the y-intercept is typically your starting point, and your x-intercept is when you're no longer going to be making money for whatever we're talking about. In this context, you're probably never going to have a function quite like this. This is, I mean, maybe, but it's not super likely. Okay. And then asymptote. So part C says, are there any asymptotes? So we have x in the denominator, so we know there's a vertical asymptote at x equals -4. And this is a vertical asymptote because x equals -4 is a vertical line. We can't cross that, right? Do we have a oblique or a horizontal asymptote? So we got to go back to those rules. Our power on the top is the same as the power on the bottom. So our asymptote is going to be horizontal, and it's going to be y equals the fraction that it forms, which is 1/1, right? Let's go up and look at the function, the original function here. This is an x to 1 power. We have a 1 in front, so it's 1/1. Okay, 1/1 or 1. So we have a horizontal asymptote. Remember, oblique is the top has a higher degree than the bottom by 1. And then you have the oblique asymptote. Remember, if it's a traditional fraction, like x over x squared as your high degrees right on the top and bottom, then it's y equals 0. Okay, if they're the same, it goes to that constant. We've covered that in limits. We've covered that in the warm-up and the review at the very beginning. Hopefully, and you saw it in algebra, so hopefully we're getting that down. All right, that's all stuff that I expected you to learn before my class, but again, I still want to show you just in case. And then we're going to go to step 2. All right, step 2 is all about analyzing that first derivative. So let's find our first derivative. So when we go to do the derivative of this function, we know we're going to have to use a quotient rule. So we're going to have the denominator comes up, which is x plus 4, original denominator, times the derivative of the top. Well, that was x minus 4, so the derivative is 1. Okay, minus the original top, which was x minus 4, times the derivative of the bottom, which is a 1, all over the bottom squared. All right, now we need to simplify this because that's a hideous up top. We got to think of this as 1 being distributed isn't going to change it, right? So we're going to have a minus. So I'm going to change this minus sign to a plus and change both of those signs. That way I can add those terms together a little easier. So I see x plus a negative x, so the x's will cancel. And then we'll have 4 plus 4, so I get 8 on the top over x squared. I mean, x plus 8 squared. Okay, so that's simplified. All right, so then we're asked to see if we have any critical values. So we had partition numbers and critical values. We have a partition number because we cannot cross, somehow hold on. Did you notice my 4 became an 8? Just a typo. We cannot cross -4 because we have an asymptote there. That asymptote follows. Look, we can't get a -4 here. It will follow the second derivative as well. So we cannot have x equals -4 in our domain or in this whole entire problem. So we have a partition number. At x equals -4, and now we need to find if there are any critical values. Now, in terms of math, right, critical and partition numbers are just what goes on your sign chart. So, I mean, really, do I care if you mix up the names? Not really. Like, it's okay if they're all critical values or any way that you can think of them. Except when it asks what are the partition numbers in my math lab, I guess, then you have to know which ones are which. Anyway, critical values are where the derivative equals 0. So we have our 8 over x plus 4 squared. Where does that equal 0? Well, you're going to times that up and you get 8 equals 0. So there's no solution. So do we have any other critical values? No. So on our sign chart, the only number we add is -4. Okay, then we're going to put in a value into our derivative, first derivative, and we're going to find whether or not it's increasing or decreasing before or after. So if we put in something like, there's our values, right? -5, then I would have 8 over -5 plus 4 squared. That's going to be positive because anything squared is positive. Positive divided by positive is a positive. So you can calculate that all the way out if you need to. And this is a non-defined spot. Now we need to put something above, maybe 0, because that's above -4. So 8 over 0 plus 4 squared is still a positive. So this function is always increasing. But can I include -4? No. So you can't just say increasing from -infinity to -infinity. You're going to say increasing from -infinity to -4, and then again from -4 to infinity. Okay, so now we know it's increasing from here to here. Everything's going up to the right, up to the right. Hopefully that looks right on your video. Can't think of whether that's my right. Does it this way for your right? I don't remember. Okay, so I know in a classroom, but now I can't think of how it comes through. Okay, I wish we were done, but that was all of step 2. Okay. Oh, local extreme. Do we have a local extreme? Nope, because it doesn't switch from increasing to decreasing, and we don't have decreasing, so we just leave those off. You list them if you have them. We don't have them. So we're going on to step 3. Step 3. Okay, for step 3, we need to do the second derivative. So we currently have, we can see it up here, the 8 over that. So when we go to do the second derivative, we're going to have the original bottom, x plus 4 squared, times the derivative of the top. Well, the derivative of the top is 0, because what's the derivative of 8? It's 0, which is super nice. Okay, and then minus the derivative of the bottom. So the derivative of the bottom, you're going to bring the 2 out front, keep everything the same, drop that to a 1, and times by the derivative of the inside for the chain rule. But the derivative of the inside is pretty, it's only a 1. So that's our derivative of the bottom times the original top. I guess I could have wrote that on the front, but it's okay. 8, you might have written it on the front. And then we're going to square the bottom. Well, the bottom was already squared, so we're going to square a square, which is just a 4. So we like this because we do get some simplification that's kind of nice. 0 times anything is 0. That whole term just magically disappears. Then we can do 8 times 2, and we'll get 16. So we have -16 times the x plus 4. I don't need to write the ones because 1 times anything is itself, and 1 something to 1 power is itself. All over x plus 4, 2 times 2 is the 4th, like this. Now, why didn't I put the x plus 4 times through the 16? Because I can see that one of these, let me change colors real quick, that one of these will cancel with one of these, leaving 3 of these. So I can simplify this to be -16 over x plus 4 to the 3rd. So I left it in factored form to see if I could cancel a common factor. Okay. So then I got to see, where are our partition numbers? Well, we have the same partition number, and we have to look for an inflection point, right? So our partition number is still at, partition. Oh my gosh, I did a little extra in there. Do you see my extra TI? Okay, so our partition number is going to be at x equals -4 still. Okay, there we go. And we don't, where's this thing going to equal 0? Well, if I put equals 0, right, then this would times by 0, there's still no solution. So there's no inflection points where it's switching from concave up to down. So we have the -4. I'm actually running out of room. Holy moly. I even did an extra page. Let me just do another extra page because I can. Okay, so then from here, I'm going to do my sign chart and I'm going to have my -4 again, but this time it's for the second derivative. So the -16 over the x plus 4 to the third. And I'm going to put in a value. Maybe I'll put in -5 again, and I'd have -16 over -5 plus 4 to the third. So that's a negative to the third, which would stay negative, but a negative divided by a negative is a positive. So this section's positive, and this is again a non-defined. We didn't have a 0 and inflection point. And then we would put in maybe a 0 because that's easiest. So I had -16 over 0 plus 4, so it's 4 to the third. So positive on the bottom, negative on the top is going to leave me a negative. So we are concave up from -infinity to -4. And then we're concave down from -4 to infinity. All right, so I think we don't have any inflection points. You can put no inflection points, partition number, whatever. Now, what if I want to graph this thing? Okay, we're going to try to graph it the best we can without your graphing calculator. So let's go with starting at the very beginning. We have our asymptote. So our asymptote's at -4. 1, 2, 3, 4. -4. I'm going to do that as a dotted line because that's what we typically do. We cannot cross this all the way through all of our functions. And then if we scroll up from our beginning information, our intercepts, we have a point at 4, 0 and 0, -1. So 4, 0. And 0, -1. Those ones have to be on there. Okay, and then what else do we have from that? We have our asymptotes, our intercepts, our domain. So let's go to increasing. We knew everything is increasing, so it's rising to the right. Okay, and then we have concave up from negative infinity. So I'm going to do a little pointer here real quick. Hold on. -infinity to -4, right? We're concave up. So my thought is we are concave up, and then down here we're concave down, but still increasing. Okay. How else could I make sure that my two areas are what I want without a graphing calculator? What would I do? I could put in points and see and get exact values if I need to. So if I wanted to put in a value like -5 into the original function and see exactly where it is, we could. So we go all the way up to our original function. And if I put in a -5 here and here, -5, so we would have what? -5 minus 4 over 5 plus 4. That's going to give me -9 over 9. So I get -1. So if I put in -5, I'm at -1. So -5, I'm at -1. So there's a point right there. And we're increasing. Oh, we didn't do the other, that'll help us. The horizontal is at +1, the horizontal asymptote. But I thought the graph was up there, but it must be down here. So, in my logic, I thought the graphs were opposite, but this one could be concave. No, did I put in my value wrong? Did I do something silly up here? -5 minus 4. Oh, I did. I was like, dude, this isn't working. Okay, cross this out. Maybe I should double check my little math, right? -5 minus 4 is -9, right? But on the bottom, I have -5 plus 4, which happens to be -1, which gives me 9. Okay, now it is working the way I wanted. So I put this dot right here at -1, but we actually got 9. 1, I don't know where 9 is. It's way up here. Okay, so our graph is going to look like this. And yet, you're not ever going to be, I mean, you're going to be close. When you graph without the calculator, you're going to get close. You know this has to be concave up, but it has to be rising to the right? So I know I'm going to do this in red. I know, or purple, whatever. This can't be it because that's concave down, right? I can't cross my dotted lines. I know I can't have this section because it's decreasing. So purple is out, and that has to be those black sections. Okay, let me show you what the actual graph looks like on Desmos. So I do division right off the bat, and it was x minus 4 and x plus 4. And ta-da, there's our graph. And it looks pretty similar to what we have. If we want to add those asymptotes, it was x equals -4. That's that asymptote, and y equals 1. See how they get close to those, and we're in those two sections. Perfect. And you can even see where it crosses the axis there. And the other one crosses here. Couldn't visualize it with that red there, but there we go. All right, so using a graphing calculator is totally acceptable, except you're going to have one problem on the test that it'll say, put your graphing calculator down and do this without it. So if you're online, you're going to show me your graphing calculator that it's going away from you, and then do that problem. It's at the end just for that purpose. And you'll have to do all of this parts. You have to list every single piece. Okay. Let's see. So this next one is pretty similar. Let's do, these take so long. I'm only going to do a couple in this first initial, and then I have a second video with more examples if people need, and then the book also has more examples. So let's do an E one because they're tricky, right? So 3, we are going to do our domain and our intercepts. I have to keep my list over here because I forget what the heck it said and all that. Just the domain and the intercepts, right? And the asymptotes. All right, so let's look at this. We do have an asymptote at this one. I don't know. Okay, let's just look at our domain. All right, so start with your domain. I'm going to go back out to normal view here. And our domain of this is, we don't have, we can put anything in, right? And get anything out. Well, range would be blocked by 0. Can an E to something ever equal 0? No. So we are blocked by what we get out of the function, but we can put any number we want in there, a negative, a positive. It's just a number to a power. So our domain is really all reals, which you have often in a lot of your functions, unless you have an x in the denominator or a square root where you can't be positive, or you have to be positive. So there's our domain. X-intercept, let y be 0, right? So x-intercept, you're going to let y be 0. All right, so we're here, and can that ever equal 0? No. It's tricky, right? If I put 0 in, I get 1. Any number to the 0 power is 1. So there's no solution. And that's something we've had quite a few problems on now, because there's no solution there. This graph can never cross your x-axis. So it's all above or all below. All right, y-intercept. Y-intercept, you let x be 0. So y equals e to the negative 3 times 0 squared. So e to the 0 basically is 1. So we have the point. We put in 0, we got out 1. Perfect. What was the last thing? Asymptote. We can't get out 0. So we actually have an asymptote at y equals 0. I don't know if you learned that before. How would I'm not sure. You're not required to list that asymptote. We'll just leave it at that. Maybe, I don't think you are in your homework. If you are, it's at 0, but gosh darn it, I can't think of if you learned that. We won't worry about it. Hopefully you learned about asymptotes for ease, but I'm not sure. Okay, so we have that information. Now let's look at the first derivative. This is step 2, first derivative. So the derivative of this sucker that we have is going to be the big idea, e to the power. What's the derivative of e to anything? Or e to the x, e to the u, however we want to think of that. It stays e to the u, right? So it's going to stay e to the negative 3x squared. But then to take care of the fact that it's not just an x or just a u up there, is we take and times it by the derivative of the inside. And so 2 times negative 3 is negative 6x. You could set it up with the u's like we show in class. We showed in class. You could also do the way the example button does it's really hairy, but I try to think of it as what's the big idea and then times by the derivative of the inside. So we could rewrite this to be negative 6x e to the negative 3x squared. That's our derivative. Now, to find our critical values, we have to set this equal to 0. Okay, so critical values. Do we have an x in the denominator? No, so we don't have a partition number that follows us. So where does this thing equal 0? So 0 equals negative 6x e to the negative 3x squared. So we already know the e term. It can't, if we thought of this as 2 factors, which is exactly what it is, the e term can't be 0. So we can basically ignore that and just look at this term. Does that factor, where does that factor equal 0? So we would divide by negative 6 and get 0. So we can see that this term can't be 0, right? We keep seeing that over and over. So we have a critical value at 0. So we'll set up our sign chart here at 0. We're going to then, take our little x and our y and put in a value below 0. Maybe we'll do negative 1. We put this is all about the first derivative. So we're putting it into the first derivative, which is this whole thing here. So negative 1, negative 6 times negative 1 times e to the negative 3 times negative 1 squared. Is that positive or negative? Well, it's just cheap. I got positive in my homework. Yeah, because you're going to have a positive times that. It's going to be positive. You could just put it in your calculator. And this is a 0. Okay. And then a number above 0 is maybe 1. And then we do the same idea and I get a negative. This is a positive. So this was a negative. So we are increasing and then decreasing. So do we have a local max or min? We do, because we switched from increasing to decreasing. So it's going to have a maximum. Okay, so local max at x equals 0. Increasing. It's increasing from negative infinity to 0, and it's decreasing from 0 to infinity. All right, second derivative. I got to add another little page on here. Add a page. So second derivative is going to be, I got to look at that first derivative. Do I have no other people to look at? Yeah. So second derivative, we got to look at that piece, right, of x is going to be a quotient or a product rule because you have a negative 6x times an e part. So Maybe I'll just write that here so we can kind of see it. It was negative 6x e to the negative 3x squared. So we can see this is like a time. So we have two factors. We just looked at that. It's two factors. So the original first is negative 6x times the derivative of the second term. We've already done that before. It stays exactly like we see it, but then we times by the derivative of the top. That's going to give me negative 6x. We're like this. So original first, derivative of the second, plus the original second times the derivative of the first, which is just negative 6. So there's our second derivative. Now, I know for setting this equal to 0, I can't keep the e terms in there because we'll have to factor that out because they can't equal 0. So I'm going to write e to the negative 3x squared here, parenthesis. What do I have left? This term, these are all times, and there's our plus. So this term is going out front. I have that left and that left. So 6 times 6 is 36. Negative times negative is positive. So 36x squared is left there. Now over here, we have this term coming out front, right? So I only have negative 6 left. So you can write that as minus 6 or plus a negative 6, don't care. All right, we're here. Now, where does this equal 0? This term kind of just disappears, right? It can't be 0. It doesn't have a solution. So our only hope is that this part right here will have a solution. So we'll add the 6, divide by the 36, and then we have to take the square root of that. Ooh. Can we have a decimal? I think it'll let us have a decimal. I was just thinking, well, if we did this, right, the square root x would equal plus or minus the square root of 6 over the square root of 36, which is the square root of 6 over 6. That could be your answer, positive or negative. Don't forget the positive or negative. I like the fact that I can just put it on my calculator. On my notes, I have negative 0.41. And I have 1/6. I like this. This is simplified the right way, but okay. So I'm going to put it in, make sure I got negative square root of 6 divided by, oops, I don't want it inside, divided by 6 is, yeah, 0.41. So this is about positive or negative 0.41. It's like 0.082 something. Oh, yay! These are our asymptote information, or not our critical value. So I have negative 0.41 and positive 0.41. These are all of the second derivative. I always label because I forget what the heck I'm doing, right? First derivative. Am I first derivative or second derivative? Label. Okay, put the values in. You'll see positive, negative, positive. These are both zeros. They're not non-defined. So concave up is from negative infinity to the negative square root of 6 over 6 if you need to have it exact. Okay, concave, or you can put 0.41 if it lets you. Concave, oh, wait, we have two ups. And we're concave up from positive square root of 6 over 6 to infinity. Oosh, I squished it in there. It's all very pretty. Okay, there you go. Concave down, that's going to be negative square root of 6 over 6 to square root of 6 over 6, or negative 0.41 to 0.41, that middle section. Oh my goodness. So how the heck are we going to graph this without any information? Well, we know there's an asymptote. I'm going to make it red just so you can kind of see it here at y equals 0. That means you're not crossing that, okay? And we already knew we weren't crossing the x-axis anyway. It's an asymptote, but we knew we weren't crossing it because we found there was no intercept. But we did find an x-intercept at 0, 1. I mean, excuse me, a y-intercept at 0, 1. So at 1, we're right here. Then we know it is got a local max at 0. So at this point that we just graphed, that is a local max. We know that because it was just at that spot. We know that there is at x equals 0, a local max. Okay, what was the other things that we knew? We have increasing to 0. So this whole section here, this whole section, whatever we draw, is increasing, rising to the right. Okay, this section over here is decreasing, falling to the right. So I can visualize kind of something. Then we know that that has to be going to a tip at this dot right here. And we know it's concave up and down. So let's imagine this is 1 and -1. We can imagine then our -0.41 and our positive 0.41. So we have those two values, and we know at those values, we are switching from concave up to down. Now, remember, that's not at the point on our U, it's the point when, so here I am, I'm curving, right? It's the point that you start to change directions to the other concave. If we're at the point, that's a max or min, you know, on our swoops, right? So this point is when we're switching from concave up to down. So I visualize I'm concave up. So I'm visualizing this to be kind of up, and then right here it's switching to be down and vice versa. I don't know if that's the best graph, but like that's what I'm visualizing. I'd give you 100% on the test if yours is as pretty as mine. I would know you're getting it. You're understanding concave, increasing. Are they going to be exact? No, but it is kind of hard. Let's look at the Desmos real fast. Let's put in what the heck was our original? Something way easier. E to the power, I got to go back. Okay. To the power of -3x squared. Be careful when you use your regular graphing calculator. I use Desmos just because it's an app and it's really easy for me to show you. When you use your graphing calculator, you have to use that negative sign at the bottom for in front of the -3, it'll give you an error. So in front of any number, use this negative down here. Cool, there it is. And this inflection point right in here is at 0.41. It won't show it exact, but right in here. That's where we're switching from going down to up. It's right in there. Okay, so we can kind of see that. Yeah, my graph's not that bad, but I don't get close to the asymptote like I should have. My graph's a little crappy, right? Sorry. And my U shape is not pretty. All right, there we go. So again, there are a couple more problems that I'm going to do in a separate video. I think I have them in there, or if there isn't, you can look at the ones from the company as well. A lot of this we've already done. It's putting it all together. We're going to spend 2 days on it and do an activity as well. All right, that's all I got for you.